For once I've gone to Bismarck and it's actually cooler here than it is in Fargo. So I'm missing a day where we've got full sun and a nice gardening day potentially. But I'm still happy to be here today, and I'm going to be talking about the science behind indoor plant lighting. So how many of you are in the market for indoor plant lighting? Do you find it kind of confusing as to your options? Well, and I'm going to hopefully illuminate this particular subject and teach you the terms that you need to know to do this successfully. Now, before we begin, I'll start off with our non-discrimination statement from NDSU. So we treat everybody well at NDSU. But here's what I'm referring to. Now, if you go out and you're trying to buy lighting to start vegetable seeds or to add supplemental lighting when it comes to foliage plants, you'll find that it's really complicated. And that's because there are so many terms out there. You know, you read the box and you're like, what is this that I'm looking at? So I'm going to tell you it's complicated, but I'm going to break it down step by step so you can learn what your lighting options are and so that you can determine how best to grow plants. So let's think back to like 7th grade biology. So what do we need for plants? So plants, they take up water and they take up carbon dioxide from the atmosphere. And then they use this for the process of photosynthesis. So they undergo all these chemical reactions, and then they produce carbohydrates, so sugars and starches, and they produce oxygen. So all of you probably are very familiar with photosynthesis, but you may fail to remember a very important input here is light. Without light, plants can't grow, and they cannot photosynthesize. When it comes to lighting, you need to know just a little bit about physics. And I promise, I'm going to keep this very simple for you, but light acts both like a particle and like a wave. So particles of light are called photons. So you've probably heard of photons. And that goes to light quantity, goes to the intensity of lighting. But there are also wavelengths, and that goes to the color of the lighting. So you may have noticed LEDs out there that have different color of bulbs in there, right? So we're going to handle 3 aspects of light. First, light quality, so the color of those wavelengths of light. We're going to discuss the intensity of light that is falling on your plants, and then how long you should have the lights on. And all of that is going to equal the daily light integral. I'm going to first start off with an analogy. And this analogy, I'm going to talk about rainfall. So say, for example, you're putting a bucket outside to collect rainwater for your houseplants. So why would you do that? You may want to do that because you think that rain will be a higher quality of water than your municipal water source. And that can be because there's no chlorine in rainwater, there's no fluoride, and we've definitely had plants that are sensitive to that. So that goes to quality, the quality of the rain falling in our bucket. The next component is intensity. So we think about rain as it's falling. You can have a light mist, you can have a sprinkle, and then you can have a downburst of rain. That goes to the intensity. But intensity doesn't mean anything if you've got a downburst, but it only lasts for 5 minutes. So that's where duration comes into play. And that, you take quality, intensity, and duration, that's inches of rain per day. So I'm going to use this analogy, but use it with light. So first off is light quality. We're going to discuss the different wavelengths that are important. As you look at this chart, first focus on that top bar. So on that top bar, as we go from left to right, we've got the shorter wavelengths on the left-hand side, the longer wavelengths on the right-hand side, and the visible spectrum is that little sliver in the middle. On the left hand, with the shorter wavelengths, those have more energy. So we know that it has energy with gamma rays because nobody wants to be exposed to radiation. We also limit exposure to X-rays, And think about ultraviolet. There's a lot of ultraviolet energy in the sun, and that can cause sunburn. So we know there's energy there. And then as we go across the top, there's less energy. But I wanted to point out infrared wavelengths, and that's responsible for heat. Now, don't worry. We're not going to be focusing on that top bar. We're going to be focusing on the light that you see there. That very little sliver, that's the visible spectrum. And today you're going to be getting very familiar with the types and color of light that your plants need. You'll notice kind of the purples and the blues are between 400 and 500. You'll notice this green light in the middle, and red light is like between 600 and 700 nanometers. I can see some of you are looking a little skeptical right now because this is getting very technical. Don't worry, I'm going to really break it down for you. So let's take a look at this table. So once again, we've got our blue light between 400 and 500 nanometers. And you'll notice that that's very important because plants need blue wavelengths for photosynthesis. It's very efficient for them. We've got green light. Green light is less efficient for powering photosynthesis, so they don't need as much. And in fact, plants reflect green. That's why they appear green to the human eye. And then we get into red light. Red light, once again, is more efficient. We also have far red, and I'll discuss that in the next slide. What would happen if we were to grow plants only under a single color of light? So if we grew plants just under blue light, they would be really short, really compact, not much growth in between the leaves. They would have very small leaves, but it'd have a decent root system, and it would be well branched. If we grew plants just under red light, they would be taller with bigger leaves, but they would not be well branched. The root system wouldn't be as nice. We do know red light does help induce flowering and fruiting. What about far red light? Far red light is what a plant experiences when it's being shaded by another plant. So the red is being filtered out, and they're only receiving far red light. What happens in that situation is the plant knows that it's being shaded. It knows that it needs to grow fast to grow out of the shade and get light. So when we give the plant too much far red light, the plant is not going to be healthy. It's going to be too tall, it's going to be stretched and lanky. But what if we grow using a combination of lights? Blues and reds and just a little hint of far red. That plant is going to grow well, it's going to be compact, well branched, and have a nice root system. In addition, if you're growing, say, like a plant with different colors, like a red lettuce, it's going to color up too because of having that nice combination. So one of the terms that I want you to know, and it's going to help you when you go to buy plant lighting, is the term PAR. It stands for photosynthetically active radiation. You don't need to know that term. What I want you to remember is just the abbreviation PAR, because that's what appears on packaging, and it's the measure of useful light to the plant. So looking at the figure that we have here, you'll see that the plant for photosynthesis is using a lot of blue light, which is between 400 and 500, and it's using a lot of red light, which is between 600 and 700, and it's using less of the green wavelengths. So this is the useful light to the plant. This is what helps it grow and be healthy, and that's measured with a spectrometer. So how does this translate if we're looking at the sun, or if we're looking at incandescent bulbs, fluorescent bulbs, LEDs? How does this relate? So this is where we're going to apply what we learned here with physics. We're going to look at the spectrum. Now the sun, of course, is going to be your very best source of lighting. You're going to see that it has lots of blue light, it has lots of red light, and then of course it's got all this other energy. But we live in North Dakota. We can't grow our plants outdoors for 12 months of the year. So we need to start looking at artificial forms of lighting. Has anybody tried to grow plants under incandescent lights? No? Well, that's a good thing, because incandescent lights, if you look at the spectrum, it's not good for plants. You'll notice that the useful spectrum, blues and reds are low. It's got a whole lot of far red light. When you grow a plant under incandescent light, it thinks it's growing in the shade of another plant. So what's going to happen? It's going to grow very tall and lanky, and it's not going to be what you want. In addition, we're phasing out incandescent light bulbs because they're not energy efficient. They give off a whole lot of heat, which is actually wasted energy, and they've got a short bulb life. What about fluorescent lights? Fluorescent lights were a great improvement over incandescent bulbs, both from energy efficiency standpoint, but also from plant growth. So our fluorescent lights produce less heat, there's less energy wasted, and they can be placed closer to plants without burning them. So you can place fluorescent lights closer to the canopy of the vegetable starts that you have, and it won't burn them. Now, the exception would be compact fluorescent lights. Compact fluorescent lights do give off more energy than the tube lights. Fluorescent light bulbs last a whole lot longer than incandescent. They produce more light in the useful spectrum, or PAR. But there's a problem with fluorescent bulbs. Fluorescent bulbs contain mercury, so we have to recycle that as hazardous waste. Here is a spectrum for a particular fluorescent T8 light bulb. So as we look at the spectrum here, you'll notice that between 400 and 500, so this is the blue light area, there's a nice big spike here. So this works quite nicely, and then we've got a fair amount of red light in this spectrum. So this is a fluorescent T8 bulb with a natural sunshine or daylight spectrum, and that works very, very nicely for lighting seedlings. We've got 3 different types of fluorescent lights that are out there. Going across from left to right, we have the T5s, the T8s, and the T12s. Let's start off with the T12 on the right. Now that's the older of the bulbs, and it's got a diameter of about 1.5 inches, so we're seeing less and less of this, and that's the least efficient in terms of energy. It produces 50 to 70 lumens per watt. T8s, that's more commonly used in your shop lights and such, and people have been using this for plant lighting for a long time. That's got a diameter of 1 inch, and it's got 80 to 90 lumens per watt. So that was a great leap over the T12s. Now we have the T5s. The T5s are thinner and more efficient, producing up to 100 lumens per watt. With the T8s and the T12s, if we look at the prongs, it's at the same distance between them, so these will work in the same fixtures, but not for the T5s. The T5s need their own fixture. So you'll see a lot of plant lighting that's now going to the T5s because they're more efficient. You'll see some bulbs out there that say T5HO. HO stands for high output. So you can look for the T5 HOs in the full spectrum, and those tend to be quite efficient. How many of you are growing under fluorescent lights? Nothing wrong with them. There's nothing wrong with growing under fluorescent tube lights. They're still very useful. You've got some options. You can use like a daylight spectrum, like I showed you the spectra of. You can mix one cool white and one warm white, and then you would place them 3 to 6 inches above your seedlings. You want to place them fairly close to the seedlings so they receive more light. But as those seedlings grow, you got to raise them up. Although fluorescent lights don't produce as much heat as incandescent, they can still burn the plants if they're touching, particularly in the area where the ballast is. So we do need to move up the lights as the seedlings grow. We don't want them touching the light. Here's one thing people don't think of, and that is the bulbs do decrease in intensity over time. If you're finding that your bulbs are not if you find that your plants aren't growing well as previous years, you may want to replace your bulbs every year or two. So just showing you a standard setup here. So we've got, steel shelves here. We've got the lighting 3 to 6 inches above the microgreens. Down here, it's a little bit higher, and it's just been raised to show you the crop that's growing here. But remember, place this fairly close to your plant, somewhere in the 3 to 6 inch range to increase that intensity. But what about LEDs? These are light-emitting diodes, and this is another great improvement over fluorescence. So our LEDs are very energy efficient. They produce less heat than fluorescent and incandescent, and then they have a longer bulb life. One downside is that it costs more to purchase an LED setup, but that is coming down, and it's come down greatly over the last 5 years or so. Some of our LEDs can be very intense as far as the amount of light that they produce, and they can be hung further away from the plants than the fluorescents. But some of them do emit a fairly narrow spectrum of wavelengths. So everybody wants to know, can you use a household white LED to light your plants? And I would say no, and the reason is that the household white LEDs have been optimized for the human eye. They have not been optimized to produce the right colors for the plant, the right wavelengths. But let's show you the first generation of LED plant lights. Yes, question?
If you're using these like LED shop lights, a lot of them have like a plastic diffuser on there. Should you remove those diffusers to give more light to the plants then?
You can. So the question is, should you be removing the diffuser to increase the light intensity? And you can. And then there are other fixtures out there that will actually direct the light more downward too. So there's also that possibility. But if you've got a diffuser, you could certainly take that off to increase the light intensity. So here's the first generation of LED plant lights. So what do we notice here that's different than the fluorescents and the incandescents? It's red and blue. They're trying to optimize the right wavelengths that the plants are receiving. Any of you have this? No? You do? Yes, some of them. The one issue with this is that industry no longer likes this particular setup anymore. And that's because if this is your sole source of plant lighting, say for example you're growing in a basement or you're growing in a growing tent, it's the color. It's really hard to work under this color. So we've got a term for this in the industry. It's called blurple. So blurple is what they call this color. It's really hard to use if this is your sole source of light. Now, if you're growing next to a window and it's kind of diffused by natural sunlight, it's easier to grow with. But if this is your sole source of light, if you're growing, say, like in a vertical farm, people get really tired working under it. It irritates the eyes, and it's hard to work with the plants. Can you imagine? So we've got, what do we have here? Can you even tell? Lettuce. It is lettuce, but it doesn't look right. And it's hard if you're a grower to determine if there are any plant problems. Say for example, there's a nutrient deficiency, so it's starting to look yellow. Hard to tell under this red and blue situation. So the plants look black. It's hard to tell if you've got an insect problem. So this has become outdated. So we've got the next generation of LEDs, and we're calling this warm white. So with the next generation of LEDs, we've got 4 different kinds of bulbs that are here, and we've got different terms. We've got the orange bulbs here, and this is at the 3,000 Kelvin range, and we'll talk about that in a minute. We've got bulbs that are more white to blue, that's in the 5,000 Kelvin range, and then we've got these These other lights that have red with the white dot in between, these are the red lights at the 660 nanometers. But we'll also have two small dots, one here and one here, to add just a little bit of far red light to make sure that our plants are growing. So we've got 4 different types of bulbs here, and instead of having that blurple look to them, we've got more of a warm white look. This is a high intensity fixture, and if you turn it upside down, so it's actually shining down on the light, it shows white from the side. So a whole lot easier for gardeners to work under. But we did introduce a new term here. We introduced the term Kelvin. So there's the Kelvin scale, and this is less helpful. I wish that they had talked about this in terms of par, but we've got light in the 3,000 range, so it's getting more towards the red or the yellows, and then the 5,000 range is getting a little bit more towards the blue area. But the Kelvin scale is meant more for humans. It doesn't necessarily reflect the wavelengths that the plant perceives, per se. But it still gives you a little bit, of information as to the color of the light. In general, lower numbers, you're going to have warmer, redder light. Higher numbers, cooler, bluer light. Fortunately, industry is starting to put the actual spectrum on the boxes of the plant lights that are out there. So this corresponds with the light that I just showed you, and it's got a nice blue peak here, lots of red light, which would be great, particularly if you're wanting to grow something that will actually produce fruit indoors, and then it has a smidgen of near red light. So when we turn the device off, this is what it looks like. This is what we call a surface mounted device, and we've got the LEDs, the diodes that are mounted on this board, and that's what it looks like when you turn the light off. On the right is the back of the fixture. There's a little bit of room between the surface and what we have here, so that if there's a little bit of heat, it would dissipate. So we want to be looking for a surface-mounted device. We want to avoid the COBs, which chip on board. For a while, looked like the industry was going to go more towards chip on board, but now it seems to be going away from it. And that's where they've got the diodes that are clustered together, kind of like in a headlight type of structure. We have LED tube grow lights that are on the market, and this is nice because our fluorescent tube lights are made out of glass. The LED tube lights are made out of plastic. That makes them a lot less fragile. There's also no mercury involved, which is nice because then we don't have to recycle our lights at the hazardous waste site. You'll also notice that there are some LED tube grow lights that are plug-and-play bulbs. And what that means is they would fit into a standard fluorescent fixture. So if you've got a shop light, you may want to look for LED tube grow lights that say plug-and-play, so that they would fit into like a T8 fixture. So that's helpful to know, but there are also ways to kind of jerry-rig your existing fluorescent fixture to accommodate LED tube lights that aren't plug-and-play. There are various YouTube videos online that show you how to do it, and it's fairly easy to do. So that's the nice thing. You don't necessarily have to go out and buy a new fixture just because you buy LED tube lights. When you go and look for LED tube grow lights, you'll notice that they are marked with 2 different categories. Some are meant for flowers or fruiting, and what that means is there's going to be more red light and it's going to be higher intensity, which is necessary to assist with flowering and fruiting. If you need lesser amounts of light, you would look for lights that are labeled greens or seeds. So just showing you, some of the light fixtures that you'll find if you go to a big box store. So there's lots of different ones that are out there. But the very important thing is to look at the box. So I've spent a lot of time talking about color of light. Let's talk about light quantity or intensity. We're going to be introducing some new terms with respect to this. Because in addition to having the right color of lighting, we need the right intensity. It depends what you're growing. If you're growing a foliage plant or a house plant that doesn't need a lot of light, virtually anything will be good enough for that application. If you're trying to grow vegetable seedlings for transplant outdoors, you need a moderate amount of light. If you're trying to actually get your tomatoes and peppers to grow indoors, flower and fruit, you're going to need a huge, huge quantity of light. But it is possible. We can measure light quantity. So this is going to go back to the very beginning where we talked about the fact that you need to know just a little hint of physics to understand lighting. So light acts both as wavelengths and as photons or particles. So we can count the photons, using light meters and such. And you would look for photosynthetic photon flux density. Don't have to memorize that, just look for ppfd. This will occur on plant lighting boxes, and this will be very helpful as you're navigating and understanding light intensity. So it's the amount of PAR, or the amount of useful light in those specific color ranges that lands on a square meter every second. So it's kind of an instant reading. And this is going to occur in micromoles of photons per square meter every second. Sometimes you'll see this abbreviation, which looks like a backward U. For this presentation, it was just easier for me to use this particular abbreviation. So we're going to be talking about micromoles per meter squared per second. I'm showing you a light meter here. I don't expect you to go out and buy a light meter. They can be fairly expensive. I think they're a few hundred now. When I purchased this light meter 12 years ago, it was $1,100. So quite expensive, but it has come down in price, and this is very helpful. For those of you that don't want to invest a few hundred in a light meter, you can use a phone app. There's an app called Photone, P-H-O-T-O-N-E. I haven't actually tested this, so I can't tell you if it works well, but that's one of them that are out there right now. It's going to be less accurate than the expensive light meters, but it'll get you in the ballpark, which would be good enough for you as long as you're not trying to make your living growing plants. So we've introduced the term ppfd. Now let's put this in perspective. So I'm going to give you a range here for anywhere from 4 to 2,000. If you're outdoors in your garden standing next to your tomatoes, let's say it's July 1st, you're probably getting around 2,000 micromoles per meter squared per second. If you stand in the shade of a tree, you're only receiving 20% of the light out in the middle of your yard. It's only 400. Oh, what about a December day in North Dakota? We're lucky if we're getting 50 micromoles per meter squared per second. Now let's shift to indoors. A south-facing window. Now there can be a range here. You're going to get more light in midsummer than you would on January 1st. But let's assume maybe somewhere in the range of 50 to 100 micromoles per meter squared per second. Or an office with a light, overhead light and a window, you're down to maybe 20 micromoles. I'll tell you, in my office at NDSU, I set up my light meter, I had only six micromoles in my office. And then if I'm working on my kitchen table at home with a table lamp, maybe 4 micromoles. So showing you how light deprived we are indoors versus outdoors. So as we choose our lighting, we need to think about the application. If we are growing on the main floor of our house, right next to a window, in that situation, you're using your grow light as supplemental lighting. So you're adding to the existing light that you have. So your choice of light is not as crucial as if you're growing in your basement with no windows. So for supplemental lighting, you can easily get by for $25, in the $25 to $50 range. If you're using your lighting as sole source lighting in your basement, you're going to have to do more research, and you'll have to spend more money to make sure that you're getting the right spectrum, to make sure that you're getting the right light intensity. So you're going to need to research this. You also need to think about where you're placing that light in relation to your plants. So the further away you are, the less light there is. In fact, there's a term for that, and it's called the inverse square. So let's just assume that you've got a fairly intense light over your plants. At the 1 foot level, it's giving off 200 micromoles. If you move that to the 2 foot level above your plant, you're only going to have 1/4 of that light. So 50 micromoles, and that's because the light is being dispersed. It's not just going straight down, but now that it's higher, it's being dispersed over a greater area. If you raise that to the 3 foot level, you're getting 1/9 of the light, hence the inverse square. So that's light intensity. Moving on to our third factor, which is light duration. This is going to go to the number of hours of light that your plant is receiving. And that's the photo period. That's the number of hours of light that's falling on your plant for each 24-hour period. Sometimes when we talk about photo period, we could use photo period to stimulate flowering. And say, for example, you're trying to get your poinsettia to rebloom. So you've kept it and you want it to rebloom again. You could give it a certain photo period. And here we're talking about getting it induced to bloom again. So you could give it 8 hours of light, 16 hours of darkness, and that can induce flowering in poinsettia. Similarly with like your Christmas and Thanksgiving cactus. But that's just a little sidebar. For the rest of the presentation, I'm going to be talking about photo period in terms of total quantity of light. So we're trying to fill that bucket. So going back to our bucket analogy, we're trying to fill that bucket with as much light as possible. So longer hours of lighting can offset lower intensity lighting. So to put this in perspective, you can have, say you've got 4 T8 fluorescent tube lights growing 4 or 5 inches above your crop. You may need to leave the light on for 16 or 18 hours per day to get enough light. If you've got a high quality, high output LED lamp, you might only need to light for 8 hours because the intensity is so strong, you only need 8 hours. Or you might have a cheap LED that's really not giving enough light, and you can't leave it on for enough hours in the day because you don't have 34 hours in a day, you only have 24. So in general, you can have the lighting on for 16 or 18 hours per day for vegetable starts without harming them. We don't want to go full 24 because plants do need to rest a little bit. They need to conduct respiration. Be a little careful with lettuce and spinach because if you're growing them in a situation where it's a little on the warm side, you can induce them to bolt or flower if you're getting into 16, 18 hours. But for the most part, most of your vegetable seedlings would be fine at 16 or 18 hours a day. You don't have to go and turn your lights on and off. You can use a simple light timer. So now we're going to bring it all home. We're going to talk about daily light integral. So we've talked about colors of wavelengths. We've talked about intensity. We've talked about the number of hours per day that you're lighting your plants. Now we're going to get to daily light integral, which takes into account all of this. If you have PPFD, you can, in fact, calculate the DLI. So you can take the PPFD times the number of hours the lights are on times this constant, which is 0.0036, and get the DLI. And that can be helpful as you're trying to purchase a plant, whether it's online on Amazon or whether you're purchasing one at the store. Sometimes they have the DLI figure, sometimes they have the PPFD figure. So it's not always standard, but it's good to know both terms so you can be an informed consumer. So you're wondering, okay, what's the range here? When it comes to DLI, it's in terms of moles, not micromoles. But I want to show you this. Let's look at December first. In December in North Dakota, we're getting outdoors 5 to 10 moles of light. If we skip to February, the light is returning and we're getting 15 to 20. So there's more light and we've got more hours of the day. Oh, let's skip to April. We're in April right now. We're getting 30 to 35. But as we skip to July, what are our plants getting outdoors in terms of DLI? They're getting 45 to 50 moles per meter squared per day. So, some things to keep in mind here, are these ranges. So how much DLI do common plants need? I've put together a table here to help you out. I know your head is spinning with all these numbers and such, but I've got the plants on the left-hand side. The middle column is going to be that light intensity in terms of PPFD, and the column on the right is going to be the DLI, which includes the light, the useful light per day. Let's first look at peace lily. So peace lily should be known to a lot of you. It's a very common foliage plant. And I'm starting off with this because it's a low light plant. What does it need? It needs a PPFD of somewhere between 20 and 40 micromoles per meter squared per second, or a DLI of 4 to 14, which is the light per day. How does that compare to cucumbers? Focusing on the line that has cucumber seedlings, so we're thinking our cucumber transplants that we're starting indoors. It's good to have a light intensity or PPFD of 100 to 300 or a DLI of 5 to 15. So that's getting you a range. If you're trying to get your cucumbers to produce fruit indoors, you're going to need, triple the amount of light, 300 to 600 PPFD or a DLI of 20 to 30. You can certainly compare that to tomatoes and to peppers, and those are even higher light than our cucumbers. They need more light. Some of our other vegetable seedlings, maybe you're starting your cabbage or your Brussels sprouts indoors, PPFD of 70 to 150 or a DLI of 6 to 12 should be sufficient. Are some of you lovers of succulents? All right. There may be some of you that have tried to grow succulents indoors and they really just didn't thrive. This is the reason. Our succulents require phenomenal amounts of light. So a PPFD of 500 to 2,000 or a DLI of 30 to 50. So hopefully that makes you feel better. If you haven't been successful with succulents, you just need a whole lot of light, and it's really hard to give without having a really high quality LED fixture. So here's another table to help you. So say you go to the store and you buy a plant grow light that has 50 micromoles. This is the PPFD again. This is the intensity. How long would you have to leave the light on to reach like 3 moles or a DLI of 3? You'd have to leave it on for 16 hours. If you bought a light fixture that had a PPFD of 100 and you wanted to grow vegetable starts, have to leave that on for 16 hours. Say, for example, you've got tomato seedlings. You may want to upgrade to provide 200 micromoles of light. And then if you're going to grow tomatoes and actually have them produce inside, you'd want 500 micromoles per meter squared per second and leave it on for 16 hours. How would you interpret this on a box? So this happens to be the light that I bought. It cost me about $60 at a big box store. Look at the output, and it's giving you the intensity, the ppfd, at 3 different heights. Here's 6 inches above the plant, here's 12 inches, and here's 18 inches. You can see that at the 6-inch level, it's producing a huge amount of light. You could actually get tomatoes to flower under it. At the 12-inch, this is still producing, at the 18 and the 12-inch, it's still producing a fair amount of light and would be absolutely fantastic for any sort of vegetable seedlings that you're growing. But it might be overkill. You could go a little bit cheaper and still produce enough light for your seedlings. Here's another light fixture I found online, and this is the Sun Blaster horticultural lighting. It's giving you figures at the 6-inch mark above the plant, so you're lighting it at 6 inches above the canopy, and if you look down here, you'd be looking for the ppfd. It's telling you it's giving you 242 micromoles per meter squared per second. So very, very respectable. And here it's showing you the same light fixture hung 12 inches above the plant. You know, it's half the light, you know, at 116 micromoles per meter squared per second. So using what we have here, you can look at those boxes, you can compare it to what's in this particular presentation and see what you're getting. This happens to be the GE Grow Light box. It says for seeds and greens, and on the very front, it's got a ppfd of only 52. So you may need to buy more than one of these and put them fairly close together to get enough light, or this would be used as supplemental lighting. But it gives you what you need on the box, but I wish they were a little bit more transparent and would have standardized language and figures that they show on the box. Because it's really hard for consumers, isn't it? Really hard to know what you're getting. But either look for that ppfd or look for the DLI. For those of you that don't have plant grow lights, you can use your eyes and observe plant growth to know how well you're doing. So how do you know if your plants aren't getting enough light? If your seedlings are leggy, that's a good symptom that you don't have enough light. You know, so they look really stretched and unhealthy. Like if they're bending towards the window, that may be a sign they're not getting enough light. And eventually they may not flower or set fruit. Conversely, you can have too much light. You know, say that you're growing too close to the light. The leaves can look scorched, or you may even drive out the chlorophyll, so your leaves will look kind of bleached. Those are symptoms that you've got too much light. You may even see abnormal leaf reddening and excessively compact growth. So we're trying to thread the needle between too little and too much light. But you can watch your plants and see what sort of symptoms that they are giving you. So if your plants look healthy, if they're nice and compact and not overly leggy, then you've hit the sweet spot. So in conclusion, these are the questions to ask yourself. You know, what sorts of plants are you growing? Are you growing low-light house plants? Are you starting vegetable transplants for your garden? Or are you growing those really difficult succulents? That's going to help inform what sort of lights. Do you need supplemental lighting, or are you growing in your basement and this is the sole source of lighting? What's your budget? Are you growing just for the short term, or are you using this light a lot and it'll eventually pay off for you? But also keep in mind that lighting technology continues to improve. It's amazing what's available now versus 5 years ago. So we're going to continue to expect that each year there's just going to be better and better lights on the market. And then research and choose lights using these terms. You know, optimize the right wavelengths. You need both red and blue and maybe a little smattering of far red. Select the light intensity that's appropriate for your plant material. And then look up the DLI and calculate the number of hours of light that are necessary, and then adjust based on how your plants are responding to the light. So thank you. Thank you so much. And I'll take questions at this point. Yes?
I was wondering if you've used reflectors or light modifiers to change the intensity and the color spectrum.
So the question is, have I personally used the reflectors to change the intensity and to direct the light downward to the plants? I have not, but they can be beneficial.
And the color spectrum?
The color spectrum would be more reds and blues is what we would want. So in that 400 to 500 nanometer and the 600 to 700 nanometer range.
I'm thinking using like a colored reflector to change the light color.
Oh, you're thinking about using a reflector to change the light color. I have not tested that, so I can't respond to that. Others? Does anybody, oh yes.
What about if you have a greenhouse outside, like one of those cheap ones you buy that's got plastic on it and stuff? Does that reduce the sunlight intensity?
So the question is, if you're growing in a greenhouse that's got plastic film, kind of like polyethylene, can that in fact reduce the intensity from the sun? Yes, it does. I can't remember what percentage. I think if I remember correctly, it's probably, you're getting maybe 60 or 70% of the light from the sun, but I can't remember the exact percentage, and it does change based on the poly that you're using and if there are in fact any coatings on it. But yes, if you're growing in a greenhouse, you're definitely getting more light than you have indoors, but less light than outdoors because of the fact that you're growing through plastic, and that does block some of the light. Great question. Others?
How about if the plastic, I have a greenhouse that started out with the plastic you can't see through.
Okay.
Well, then the first hailstorm took out half the roof.
Mm-hmm.
And when I replaced it with plastic that's clear like glass.
Okay.
So that's going to be, I mean, that's obviously going to be more light.
So the question is, we've got an individual here that was growing with a plastic that was a little bit more opaque, so you couldn't see through it, versus one that is more transparent. There's going to be a difference as to the amount of light that is transmitted between them. And you can actually look up the film that you purchased and what percentage of the light is being blocked by it. But there's differences, and it's going to depend on company and it's going to depend on product. But you definitely can look that up.
So even if it's clear, it still isn't like if the plants were sitting outside of that.
So the question is, if you're using extremely clear plastic, is it equivalent to growing outdoors? And the answer is no. There's still some light that is being blocked and is being reflected out. So there's really no comparison between a greenhouse and outdoors per se. But you can still have a lot of light going into your greenhouse. And you also have the long days too. So a greenhouse situation like that is going to be a whole lot better than growing plants in your basement or growing on the first floor of your house. In greenhouse situations, yes, you can buy lights to supplement, depending on the time of year. If you've got a year-round greenhouse, people do buy supplemental lighting, particularly to use it, during the fall, winter, and early spring months to enhance the amount of light. So with commercial greenhouses, that's certainly a thing. Yes?
Just a comment, I found that most clear plastics filter blue light.
So we've got a comment saying that clear plastic can filter out some of the blue light. And I believe you. I believe that can filter out some of it. Mm-hmm. But you definitely need to read. If you're buying plastic for a greenhouse, they'll have specs on that. And that will be quite useful. Yes? Go ahead.
On the second to the last slide, you talked about too close to the light and normal leaf reddening.
Mm-hmm.
So, in regards to succulents,
Mm-hmm.
I know that when they're stressed, they turn red. Is that a bad thing for them? Because I also read about people, changing the light to bring out the different colors in the plants.
So the question is with respect to succulents. I had a comment in there saying that plants, when they're stressed, can turn red. And the question is whether is this a good thing or a bad thing in succulents. And I'm going to say that it's going to depend on the succulent, but there's more than one reason why a plant can develop a red pigment. Sometimes it may be because that particular succulent is meant to turn red. Other times it could be because that plant is experiencing a nutrient deficiency. Phosphorus would come to mind. So sometimes when a plant reddens up or develops red to purple pigmentation, that could be a nutrient deficiency. Other times it could be a stress response due to temperature. So it's not necessarily diagnostic. As to saying that if the plant is just turning red, that it's a factor of the light. There are other factors, so it's a little bit more complicated than that, per se, and I'd have to see your succulent and research it a little bit to know whether this was a healthy response, whether it's a light response, whether it's a nutrient deficiency, or whether it's just the normal appearance of it.
So if it would be a phosphorus, what's like an easy average person, how do I get access to that?
So the question is, what can you do if you do have a phosphorus deficiency? You could certainly add, a fertilizer. And if you look at the fertilizer label, there are 3 numbers on it. That's N, P, and the K. The middle number is going to be the phosphorus level, the percentage. So you would look for a product that does have phosphorus in it, and that would be an easy way of fixing it. With respect to succulents, succulents don't need as much fertilizer as other plants because they're used to being in a nutrient-poor environment. So I would just be a little careful not to over-fertilize either, so you're walking a little bit of a fine line with respect to it. Other questions? Yes?
Succulents need a whole lot more light. What if you'd put succulents out in the yard in direct sunlight in North Dakota? What do you think they would do?
All right, so the question is, what would happen if you were to put succulents outdoors during the summer in full sunlight? If you're growing them indoors, I would tell you, you first need to accustom your indoor succulents to being outdoors. So we wait till the weather is better, and we first put them out in a little bit of a shady environment, and then we increase the light exposure each day. If you were to take your succulents from the indoors and put them in full sun, that's too much of a shock for them. They're just not used to that. So you've got to kind of harden them up a little bit. But if you give them a week or 2 to get used to more light, they do very well outdoors. The one caution would be, bringing them indoors in fall. You've got to be careful you're not bringing in too many bugs and such. So that's one of the dangers of putting your indoor plants outside, is that you could be bringing in, various insects. All right, thank you very much.